Don't be so smart. So hello, welcome to the session. I'm Jonathan. I do various Perl-6 things. And this session is about concurrency and parallelism and asynchrony. So this is a very interesting area, I think, at the moment, and increasingly relevant. Why should we care about this? Well, over the last decade, hardware has changed quite a lot. My mobile phone has multiple cores on the CPU now. Back a bunch of years ago, we just had the one. We didn't, every couple of months, somebody would put out a new CPU, and there were more cycles available for us to waste by doing things at higher levels of abstraction. And now we have to do things at higher levels of parallelism instead, I guess, because we've kind of run out of that. So there's kind of an interesting being able to make use of those multiple different cores in our machine. There's at the same time been an increase in distribution of systems. Did any of you see the Reactive Manifesto that came out recently? Okay, if you didn't, go and look for it. And it's basically talking about the fact that user expectations are changing, but also the way we build systems is changing. So that increasingly we're not just building these monolithic systems, but they always pull data from different places. We have all kinds of events coming in all the time. We have users wanting to be kept very up to date. There's often a lot of push-based things that are coming along, things like WebSockets, for example. So in some sense, we're also getting more and more asynchronous, or needing to deal with asynchrony. So these are very relevant topics, they're increasingly relevant topics, and they're things that I'm finding myself talking about increasingly as part of my work as well. So one of the questions is, why now? Why has it taken us this long to really sort of, for me to come on stage and give a talk about this sort of stuff in Perl-6? And the answer kind of has been that I've wanted to do this for ages, but didn't really have the building blocks to be able to do it. And that all changed earlier this year when we got to the point of having the Rakudo Perl compiler running on the JVM. If you came to my talk yesterday, you'll know a bit about that. And the JVM provides a whole bunch of the things that we need to work on this. It's got threads, which have been used widely in industry for a lot of years. It's very mature. We don't have to spend time guessing, has it screwed up or have we? And it also has a whole bunch of stuff, including some of the latest stuff in the latest versions of the VM, for doing asynchronous I/O of various kinds as well. So we've basically got the building blocks we need to start saying, well, let's put these things together and sort of see how they fit into Perl-6. So why am I looking at this? Actually, there's something that a lot of people maybe don't know about me. So you see me here at Perl conferences talking about Perl stuff. I'm actually also a C# developer. I teach C# as part of my day job. So I'm very involved in this language as well. Now, on the .NET platform, threads are a daily reality. Now, unfortunately, a lot of developers are not very good at coping with this, which means that fixing other people's broken threaded code is a daily reality. Well, thankfully not daily, but, weekly or something. So I've been having to deal with these things for a while. You get to see a lot of different ways people get it wrong, a lot of ways people get it right. People do get stuff right sometimes, that's nice. And also, very interestingly, they've done a lot of very interesting things with asynchrony over the last release of the language. Actually, the new features in the latest C# are all about making asynchronous programming easy by essentially doing some continuation passing style stuff so you don't have to have closure after closure after closure, which gets really, really annoying. So that's why I've kind of been looking at this stuff. So before we dig into talking about the concrete things, I just want to try and define a few terms. Parallelism really, to me, is about taking a problem and saying, well, how can we break this up into pieces that we can do at the same time? That tends to then subdivide into data parallelism, where we have loads of data items, and we want to do essentially the same operation on all of the data items. And then task parallelism, where we have various different tasks that we can do at the same time, and then, together they get the result. Now, one of the nice things about parallelism is that if you actually are really in this scenario where you're taking the problem and you're breaking it down into something, you have a kind of correctness criterion, which is that the result that you get at the end should be the same result you'd have got if you did it serially. And there's all kinds of tools out there that actually exploit this. Things that try and detect race conditions based on the fact that you're doing something that would violate this property. Asynchrony is kind of different. So synchronous is the normal thing we used to. You call a piece of code, it does some work, it returns you a result. It's so normal, it's what we kind of think of as the normal way of programming. But asynchrony is where essentially all that happens when we make that call to say, please do this thing, is it says, okay, I'll start doing it. And then we get control back. And typically we get back some kind of object that represents that ongoing piece of work. So we're able to later talk about that bit of work in some way, or maybe we attach to it some kind of callback so that when the work is done, this bit of code gets run. So for example, we could be saying, okay, go and download that file. And when it's done, this is the next thing I want you to do with it. Concurrency is then very much a coordination-y thing. Concurrency is inherently coping with how you have all these different things going on at different times, and you're never quite sure what's going to happen when, or what order things are going to be happening in. But somehow you need to sort of do the correct thing anyway. This is actually, in some senses, more difficult than raw parallelism, because you don't have that correctness property. So concurrency really needs tools that let us deal with essentially lots of different things going on and orders we don't always know about or control, at times we don't know about and control, that can vary from run to run of our program. Now, of course, if you break a problem up into parallel pieces, then yes, you're dealing with concurrency in the sense that at some point you'll have to synchronize all of the different bits together again. But you still have the correctness property there. But there's this load of domains in sort of the real world. Things like, say, banking, where people can come and withdraw or pay in whenever they wish, which are just inherently concurrent. You don't actually know exactly sort of when the things are going to be coming in, and you have to deal with that somehow. So these kind of need different tools. They're sort of different problems, but we're actually pretty good at that in the Perl world. I mean, when we write code like this, okay, this is a little snippet of Perl 6 code, which is taking an array of tools and graphing out all the hammers, because clearly this time the problems all look like nails. If you look at that bit of code, in there we've got a bit of object-oriented programming. Okay, doing the method call. We're doing another method call over there with the dot name. And then we're doing some higher order programming, passing a closure. And we're actually doing some declarative programming over there. Regexes are a form of declarative programming where we just say, we'll match this pattern. In this case, just look for hammer in the text. And we don't really think about this, or at least I don't really think about this. We just get the job done. So one of the really nice things about this is it's very natural. I don't sit and have to think, well, now I'm doing OO, and now I'm doing HOP, and now I'm doing... So really what we'd like is, if we're going to be dealing with parallel things, with asynchronous things, and we're going to have to sort of manage the concurrency that's inherent in all of that, we kind of need to be able to deal with these different problems, needing different solutions, but the important thing is that we want to be able to compose. So I'm going to use this word compose quite a lot in this session. Now, what do I mean by it? Well, let's just talk a little bit about what I tend to call the assembly language of parallel programming or concurrent programming. That's things like threads and locks. And I say to the assembly language because I kind of see these things as things that are the primitives that we build actual high-level language features out of that we then go and solve our problems with day to day. I think the days where we view threads and locks as things that we directly want to use to solve a problem and as a desirable thing are kind of fading away. And that's kind of a good thing. And part of the problem is that they actually really do not compose very well. So it's the typical thing if you see a system where people have built components in the system that say, oh, I'm going to spawn 2 worker threads. Great. That works if you use it in isolation, but what happens when you put 20 of those components in one application? Now we have 40 threads. And locks are kind of worse. I mean, the thing with locks is you can take 2 pieces of code, which use locks, and individually they will always be safe and do the correct thing. And you can put them into the same application and you'll get a deadlock. Locks don't actually compose. You can't just take two pieces of code that are using locking and put them together and expect it all just to be working. So, these are really the low-level things. Now, you can, and just to add this, every bit of code I'm going to show you today is working code in Rakudo JVM. Okay, so you can actually take all of this and go away and play. But you can just do something like this. Okay, you can say thread.start, you can pass it a closure, and that will be your entry point for the thread. So of course the primitives are there, but what I'm going to say is this is your last result, not your first result. This is there if you're really sort of going and building something that's a little bit lower level. So what I really want to spend my time talking about is some of those higher level things. So let's try and take a more, if you'll excuse the pun, I don't do many of them, a more promising approach. Okay? So we have in Perl 6 this async block. Async does not spawn a thread. It'll schedule the work using a scheduler, which is actually a contextual variable, so you can actually change your scheduler if you need to. What this will do is it will take this closure here, and it will schedule it. It's actually vaguely important that it's a closure, because you might actually do this in a loop. And what it gives us back is an object that we call a promise. This gets named in various different ways in different languages. On .NET, they like to call this task. Promise has also been somewhat accepted. Future is another name. But essentially what this does is it represents that ongoing piece of work. So you immediately get back this promise. That bit of work in there is scheduled. It's finding the 10,000th prime. And what we get back is this thing that represents the ongoing bit of work. So over time, we can ask for the status of this thing. And the status tells us, has it started yet? Is it running? Has the promise been kept? Kept means, well, we kept our promise, we did the work, okay, we've got to the end, we have the result. Or has the promise been broken? That is, an exception was thrown inside of this async block. Okay, so the promise cannot be fulfilled. The work is done, but it's done in a sort of a broken way. And then you have a result method which lets you go and obtain the result from this. So we can actually maybe do this. So if I essentially, we have a perfectly good REPL over here. If I do, let's go for 4,000, okay? And what we'll do is we'll take the numbers from 1 to infinity, we'll grep to the primes, oop, I can't spell prime, and we'll take the 4,000th one, okay? So that's returned me a promise, and if I take that promise and I say status, it tells me it's running. And we could actually start another one of these, and let's do, what shall we do? Let's do 3,000 over there, okay? So that one sets off as well, and we can go back and check the status of this. Oh, this one's been kept. So now what I can do is I can take it, and instead of status I can say result, result, and there is the prime number. So it's actually been going on working on this in the background. Oh, okay. So if I schedule a couple of these, it'll be going off and using all the various cores in my machine. Now, we also have added a function await here. Now, await is kind of naively like calling .result. So one question you might have is, what if I call result and the result isn't there yet? Well, the answer is that it blocks. it's actually relatively efficient about that. It's not sitting and spinning. It's actually doing something a little bit smarter. Now, one thing you can also do is call await. If you call await on a promise or a list of promises, it waits for all of them to have an answer, and then it gives you back the results. It actually calls result on each of the promises for you and unwraps them, and if there's an exception, the exception gets thrown. This is actually allowed to be smarter than just calling result and blocking. If this is in the thread pool, this is allowed to actually yield back to the scheduler. So let's actually do something a little bit more useful. So what I have here is a little program. Okay, let's just work through it. So it's doing the say. That plus there is a reduce meta operator. What it means is I want to take the list of things that follow and act as if they had a plus between them. Okay, so add them all up. And then we're grabbing all the things in the docs announce directory. And we're doing a map, and we're turning that string into an IO handle, we're reading in the lines, and we're counting how many there are. So how do I actually do this so I can go and spread this over a whole bunch of different threads? Well, all we have to do is go and put this async in here, around a bit of work. So what we're doing now is we're mapping each of those files into a promise, which will do the line counting, and then we're awaiting them all. And await gives back all the results, and then we add them all together. And remember, this is not doing a thread for every single thing in that list. Okay, it goes up to a limit. There's a sort of pool backing all of this. So I can actually run that one. And what I've actually done is I got it set up. So we'll run it first. Okay, you see the numbers? So what we did first is we ran it serially. Okay, that was the first one I showed you, and then in parallel. And you can indeed see that it actually has managed to do that a bunch faster. And I've got the dual core machine here, so I wasn't expecting a huge speed up. It's more noticeable on my 8 core at home. Okay. So that's kind of nice, but that's not where things get really exciting. Where things start to get more exciting is when we start realizing that promises can be composed. So what's interesting about this? Well, the thing is that what we can do is we can actually create promises which are based off others. So what I've done here is I've called promise.allof, and it returns to me a promise which will be kept when all of those others are completed. And you can actually not only just use some of the built-in ones, there's all kinds of things you can do with these. So there's another one called promise.sleep. Promise.sleep doesn't actually really do a sleep. What it does is it creates a promise that will be kept after that amount of time. It's not actually blocking any threads, it's just using a sort of timer mechanism, so you can have as many of these as you want. And it basically is very efficient at that. But if you combine this with an any of, okay, so we have over here, we're awaiting the computation of this prime, and we're awaiting this sleep for 5 seconds. And if we await any of those, that is whichever happens first, what you realize is you've just actually built a timeout mechanism. Okay, so just by composing a couple of promises using this any of combinator, we get to a mechanism for doing timeouts. And we can sort of see here that we just check the status, was it kept or not? Okay, if that's that one we were waiting on. And if so, we have the result, and if not, we can say we timed out. Another thing that's quite useful to do with promises is that you can attach a thing that happens after them. And you can do this with any of them, okay? So either one that you created directly with an async block, or one that you have gotten by combining promises using all of or any of, or after a sleep. So has anyone heard of Sleepsort? It's the most ridiculous sort algorithm ever. Okay, so Sleepsort is the sorting algorithm where you basically take your list of things, you sleep that value, and then you output the value. Okay, so here we've got the numbers from 1 to 20. We have picked them in a random order. Okay, and then all we're doing is we're taking the list of numbers, we're doing a promise that sleeps for that number of seconds, and then when that promise is kept, we run this closure. So essentially you can subscribe any closure to any promise, and it will run this and it will say the number. And then we just wait for all of that to happen. And sure enough, okay, so there's our numbers, and here we are. We're sorting our numbers. So it's faster than Bogosort. It's order something. How the heck do you reason about the algorithmic order of something data-based? Yeah.
But it's linear.
Constant time. It's order 0 of a huge constant. Last time I checked, if you multiply anything by 0, the other thing about promises is you can make your own. Okay, so what we've been seeing so far is promises backed by code, promises backed by a timer, promises that are a combinator over other promises. But these are actually really your synchronization mechanism for any kind of scalar value. So you can always just do promise.new, and at any point in the future, call promise.keep on the promise with a value, at which point you will schedule any of the then things, okay? Or you can break it. Now, this has various uses, but one of the nice things you can do is you can actually start writing your own combinators because of this. So one of the things that really sucked about that timeout stuff that I showed you earlier was that actually it didn't cancel the computation. Okay, that was really kind of bad. We timed out, but we didn't go back and say, oh, stop working. So what I want to do is to write a little combinator so I can give it a piece of work like this. Okay, this is a lazy list here. I can tell it the element number I want, and I can give it the timeout. And what it will give me back is a promise that will keep trying to get up to that particular element in the lazy list. And if it cannot do so in 10 seconds, it will time out. And what I want is it will give me back a promise which is kept and has the result, or is broken because of the timeout. That's a much nicer API to doing these things. So how hard is it to write such a combinator? Just to sort of show you it in action first, before we look at the code. What I can do, okay, so if I run this demo too, okay, it's thinking about it now, and over in the code, I've currently got the timeout of 10 seconds there, and I know it does complete in 10 seconds. There you are. So what happens if I go back and change that to 5 and save it? Okay, and in 5 seconds, we timed out. Okay, well, that works. So how did I write it? Well, the first thing we do, that's the signature. Okay, we take a list, probably a lazy one. Better be a lazy one, or this is really pointless. We take the element number we want. We take the timeout. So the first thing we do is we create a new promise, and we return it, and then we also make ourselves the timeout, which is a promise.sleep. And then I just do an async block, and I'm going to try and compute the result. And then we'll do that in a moment. I'll show you that code. And then when we get the result, we keep the promise with the result. So what we're actually doing is this bit of asynchronous work. We're returning the promise immediately down there, okay? And then we're actually doing the work off in an async block. And then all we do is we just loop up to this particular position. So the way that lazy arrays work in Perl 6 is they actually remember all of the things that they've computed so far. So all I'm going to have to do in this is I'm just going to loop, that means up to, that's a way of writing the range 0 ... $n-1. And then all we do is we say, well, if the timeout promise has actually been kept, then we break and we say we've timed out, and that's the last thing in the loop. Otherwise, we try and compute the next value, and we just keep going around this loop. So now we've been able to actually write our own sort of little mechanism there for try and compute up to this index or timeout, and it's not actually that much code. And what's really nice about this is that this is a nice general solution to that problem that you could, say, package up and put on CPAN or something like that. So what I've talked about so far is all very well and good for individual single values. But there's, in Perl we don't just have scalars, we have arrays and we have hashes. So do we have any sort of synchronization primitives for these? Well, one thing that we do is we can look at channels. What's a channel? Well, it's kind of like a thread-safe queue. Okay, what you can do is you can send, which just shoves stuff into the queue. And you can then, somewhere else, receive it. And what receive does is it will block on there being something that we can take out of that. So I've got a few examples based around this, and they're all actually based on a relatively real-world project. And what this is about is, actually it was a company that makes various sensors. It's an agricultural company. Okay, so you have a farm, and you have a conveyor belt of products coming along, and you have a sampler which is just looking at this product and measuring moisture content and all kinds of other things. So what's happening, if we want to sort of simulate this, what I want to do is a simulation, what's really going on in their system, of course, is these things are coming in from the reader. And the thing is that the product on the belt is not very even. There might be a good lump of it here, then nothing, and then some product. Okay, so they come in very unevenly. So what I'm doing here is just to simulate this, I've got a loop. Yes, we have a very neat way to write infinite loops in Perl 6. Okay, so we have loop, and what we do is we just send 100 random numbers. Okay, XX is it's the repetition operator for lists, and it actually funks its left-hand side, so it will generate 100 different random numbers there. So what we then do is we do that, then we just await a sleep of either 0.15 or 0.25 or a second. You might say, why don't I just write sleep there? And the answer is, well, once await actually does yield back to the thread pool, this is a good bunch more efficient. So I have this channel now which has been having these numbers thrown down it. And then what I can do is I can just have something else sat in another, either in the main body of my program or any other async block, which is just receiving these, doing the calculation. Okay, so if I run that demo free, okay, we can see, and you can see they're not coming out at a particularly even rate. Sometimes it stops for a bit. Okay, sometimes it keeps spewing out some more numbers. So that's all well and good, but what happens if you actually have things coming in on multiple channels, and you need to somehow multiplex between them? Well, that's what select is about. So one of the other things that happened in this is that, as well as having the product coming along on this conveyor belt, every so often somebody would go and take a scoop of it and take it over to a machine where they could manually analyze it and get a slightly more accurate result than the thing that was just going along on the belt. So occasionally we had these sort of other samples coming in. So I can simulate this, and of course this didn't really happen every 5 or 10 seconds, but life is too short here. Okay, so all we're doing is we're just sending down some random number after this amount of time. So what I can then do is I can write something like this. So I can sit in a loop, and then I select, and what it does is it gives me a value from whichever channel has a value available for me first. So up here, I've got these ones coming in from the belt, okay, and what I'm doing is just computing their average there. Okay, that's the mean. So we add up all the values and then divide by the number of values we had. And if I get one in from the sample channel, okay, we get it like this. Now this code looks just a tiny bit funky to me. Because what's actually going on, you'll see that you have the pair constructor, the fat arrow, and then the thing after it is what we call a pointy block. Okay, it's a lambda. So that's a way to declare a little anonymous subroutine. Now the really nice thing about select is that it doesn't just work on channels. It also works on promises. So what that means is that we could actually create a promise which sleeps for 30 seconds and then select between having a value on either of those or the run having ended. And you don't actually have to have any channels involved at all. You could just select between two promises and see which comes in first. So if I was to run this one, what number are we up to now? 4. Okay. Then what we should see is we're getting a bunch of these in off the belt. Okay, every so often we should get a sample as well. Is one going to come? Yay, there it is. Okay. Coming a little. Yeah, it is. But there's a 30-second timeout. If I ran the right demo. Yes, there we are. Oh, and I put an exit in there, so it's blown up my nice demo harness. Oh well. Nice for me. Okay. So, ready. So one question you might have is, can I ever write a channel combinator? Can I write something that takes a channel, does some stuff to sort of, add some value to this, and then spit the results out on another channel? And the answer is, well, yes. And one of the this is getting to the juicy bit of the problem that we actually had. We were solving this in .NET, so it wasn't actually this nice to solve. But basically the problem was that doing the analysis of all of these samples is actually very computationally intensive. So if you had them coming in really fast, then it was actually much cheaper to batch them and do an analysis of these whole load of measurements than it was to try and do it for each one. In fact, it couldn't keep up. It just wasn't fast enough. So what we wanted to do was actually collect them per time interval. So we'll collect all the ones that happen in 2 seconds, and then we'll average those. So what we end up wanting to do is essentially taking BeltChan, okay, and saying, give me a channel which records all of the things that happen in 2 seconds on this input channel, and then on a resulting channel, which I return over here, give me an array of all the things that happened in the last 2 seconds. And then all we're doing over here is we're just averaging them, okay? So there we are, we're receiving it. We take the average of the average, and then I just say it was from that many. And remember that they come in at different time intervals. So if I run this one, what we should see number are we up to? 5, thank you. See, someone's paying attention. Okay, so you can see these are coming every 2 seconds. Okay, so the first one was based on 4 measurements, the second one aggregated 2, the third one aggregated 2, okay? So you can see how this is going. So how do we write this? Well, we make a new channel, which we return as our result. And then the pattern is actually pretty familiar from the promise combinator. We do an async block, so we can work on this as a separate unit of work. We create a promise that sleeps for that amount of time. We have an array, which is going to contain, or a scalar containing an array ref in this case, which is going to contain the accumulated things so far. We loop, and we do a select And we either select between something on the incoming channel, in which case we just push it onto that array where it's accumulating, or we hit the end of the time period, the 2 seconds, so we send what we've accumulated, we empty out, get a new array there, okay, because we sent the original, and then we just reset that period timer to sleep for another 2 seconds. And that's all we have to do. That's not actually that much code for a relatively sort of interesting problem with all of these things coming through asynchronously. Again, we can package these things up. So that's scalars and arrays. So last but not least, let's look at hashes. What happens if I want to actually get a hash out of the end and I want to be able to sort of get all the things reduced into a single hash? So there's a class called key reducer, which is kind of useful for this. And what it basically does is provides a way for multiple workers, multiple async things, to contribute key value pairs or entire hashes worth of key value pairs into some result hash, and then a way to reduce them down. So just to take a little example, suppose that I have a bunch of files which declare various variables, and I want to go and find the most commonly used variable names across all of these source files. What do? Well, what I do with a key reducer is I configure it with 2 things. What happens the first time we see something with a certain key? And then how do we combine values that have the same key? So the first time we see a count, we just return that. The next time we see an extra value, then, well, the function we're just going to do is actually adding it together. In fact, I could have actually just passed the infix plus operator there. So all that's saying is when a word count from one of the workers comes in, if it's the first count for that variable name, okay, just take it, and if there's a couple of them, then add them together. So then all I'm going to do is do an await, take this directory where my source files are. I've just chosen the Perl 6 core setting. Okay, and what we'll do is we'll just skip any directories. We'll do the count for that file. So what we're building up here is a hash. You can see it's keyed on the variable names we found. You can see we're matching a $, a %, or an @ followed by \w+. We're doing :g, which means global. And we're just incrementing the count. And of course, within an async, you're on a single thread. Okay, we haven't got any shared memory stuff going on inside of here. When we do contribute, we actually are getting the key reducer to deal with all of the concurrency concerns. So then at the end, after we've got all of those files counted, all we have to do is ask the key reducer for its result, which is a hash, and then just going to sort the hash, and then going to sort of print out all of the results. Okay, so if I run that, okay, so maybe I didn't spend quite long enough on this bit of code. Okay, what it's doing in res there is getting a pair. Okay, so what you do is you call .key to get the key of the pair, which is the variable name, and the value to get the number of times that it appeared. And hopefully, if we flick back over here, we'll find that it's, I need a new laptop, or a faster Perl 6, or both. I should hack on this machine so I get really frustrated. Okay, so you can see the various variable counts in there, okay? Now, one thing that, if you're very observant, you will have been realizing, is that actually I've been doing blocking I/O inside of all of these things. And you might wonder, what if we actually sent off the file to be slurped in as an asynchronous thing, as handled using asynchronous I/O by the operating system, and then we did the computation once the file had been slurped in and done the Unicode decoding and all of that sort of stuff. How would that code look? Now, at the moment, this is still very much stuff that we're in the process of putting together, okay, but this does work. So instead of having an async block, what we do is we do an async IO async file.new. We pass in the path. We call slurp. what slurp does on an asynchronous I/O object. What?
Where's the network administrator?
So, so what slurp does is return a promise. Okay, so the promise represents the reading in of this file from disk and decoding it from a bunch of bytes into a string. And because it's a promise, we can then attach a piece of work to do once the promise is fulfilled. So even this asynchronous I/O, and I know that the disk is the boring case of asynchronous I/O, it's really all about sockets and they're interesting. Okay, but we can do it here as well. So what this is doing is it's doing this slurp, it's giving us a promise, and then we're counting once we get the data in. So it's not actually a very big refactor to get to that. And because then also returns a promise, that's why we can await the whole thing. So you can chain those as much as you want. Okay, so there's a lot of stuff to come there. The only stuff we've got so far is the slurp, and also lines, which gives you a channel. Okay, it decodes each line from the file, and it spits the lines into a channel as it receives them and decodes them, which is also potentially kind of useful. So sockets should be coming fairly soon in this, and that's where things will get kind of interesting. So we actually need to get the multiplexing of those pushed down to the efficient low-level primitives. I know. Okay. Okay, so I don't have time to talk about these things that are in the pipeline. Okay, so I'll leave it there. Just some closing thoughts. There's not one true way in this area. You know, there's a whole load of different ways that we can go about doing parallel and asynchronous and concurrent programming. What I've witnessed in the real world is that threads and locks tend to lead to a lot of screw-up. So hopefully by embracing mechanisms where we separate out the concerns of synchronization and almost actor model style go and do the individual pieces of work, we actually get to something that can be a little bit more attractive. And also, this is only the beginning. Stay tuned. I look forward to sharing lots of interesting progress on this in the months and years to come. I don't have time for questions now. Harass me at the coffee break or on the boat or any time you fancy. All right, thank you very much.